Good morning, MacLaren. About 5 years ago, scientists witnessed what one called the most powerful explosion humans have ever detected, except for the Big Bang. The most powerful explosion humans have ever detected. What would that sound like? Did you imagine something like this? Well, perhaps you didn't imagine something that sounded just like that, but that was an audio representation of the first signal detected in a new kind of astronomy, gravitational wave astronomy. The event that produced it was the collision of two black holes with masses 36 and 29 times that of our own sun, spiraling into one another, joining together to create a black hole with a mass about 62 times the mass of our sun. This happened more than 1 billion years ago, more than 1 billion light years away. For as long as human beings have been here, we have looked up at the night sky and observed what was out there. First, by detecting with our eyes the visible light emitted by stars and galaxies, or light from our sun reflected by the planets of our solar system and their moons, comets, and the like. You may have observed the conjunction of Jupiter and Saturn recently, both planets lit by the light of our own sun. More recently, our understanding of physics allowed us to build instruments to perceive with light outside the range visible to the eye, extending from lower energy microwave and radio to higher energy X and gamma rays. Here's a depiction of the range of frequencies and wavelengths of electromagnetic radiation, which we commonly refer to as light. The range of frequency, like the pitch of a musical instrument, that's visible to our eyes is quite small compared to the possible range of electromagnetic radiation. Astronomers use all parts of the electromagnetic spectrum to observe the universe, with different aspects of the universe observable to different parts of the electromagnetic spectrum. Here is a conceptual depiction of an electromagnetic wave, or a light wave. It's detectable because the electric field, the part shown in blue, causes the electrons in the detector, or in your eye, to want to move up and down, just as the electric field is moving up and down. Now, a little more than 100 years ago, the German physicist Schwarzschild postulated the existence of stars so massive that even light itself could not escape them. As such, they would be invisible to us. These bodies became popularly known as black holes. That same year, Albert Einstein published his general theory of relativity that explained the force of gravity as the influence of mass, matter itself, on space-time itself. His theory predicted some astronomical observations that were remarkable departures from Isaac Newton's gravitation. One, involving the motion of the planet Mercury, was confirmed by observations in a total eclipse of the sun a few years later, and this made Einstein an international celebrity. Another prediction that accelerating masses would radiate energy in the form of gravitational waves, not unlike the electromagnetic waves radiated by accelerating electric charges. Because the gravitational force is so much weaker than the electromagnetic force, only very large masses with very high accelerations could produce a detectable gravitational wave. And even then, such a wave would require an extraordinarily subtle and sensitive instrument to detect that gravitational wave? Well, over the decades, a great effort was made to design and develop such an instrument, and here's what parts of it look like. The Laser Interferometer Gravitational Wave Observatory, or LIGO, consists of two laser interferometers. They're located halfway across the country from one another, one in Livingston, Louisiana, and the other in Hanford, Washington. As you can see in the photographs, each instrument consists of two arms. Each of those arms is 4 kilometers long. Light passing in the arm moving north and south mixes with light passing in the arm moving east and west in such a way that if the length of the arm from north and south changes from the length of the arm from east to west, that change, even a very small change, can be detected. Here is an animated depiction of how that happens. As the gravitational wave passes by, the arms in perpendicular directions alternatively lengthen and shorten. They oscillate back and forth, much like the strings oscillating back and forth on a violin. The frequency of oscillation depends on the motion of the masses emitting the gravitational radiation. And here is a graph depicting the change in time of that motion and that oscillation. As you might notice, that initially these masses are moving slowly compared to the rate at which they move about one another towards the end of this event. Here is a simulation of one black hole orbiting another. As the system loses energy, the two black holes approach one another, and as the smaller black hole nears the larger one, it orbits around it more and more rapidly. Notice that in the last few moments, the change is rather dramatic. Physicists model a collision between black holes and find out how the masses and motions of the bodies determine the wave signal produced. When a model produces the signal matching the one detected, they can infer the properties of the bodies that collided. Here are the modeled signals matching 3 detected events. And here are the inferred sizes of the black holes that produce those signals, shown on this map of the eastern United States for scale. At the start of this talk, I referred to a new kind of astronomy. With gravitational waves, astronomers can observe events previously invisible because they produce no light signal. Sometimes, however, an event that produces light also produces a gravitational signal large enough to detect. In traveling the great distance to reach us, the light interacts with the matter between us, being delayed in the process. The gravitational wave, not delayed in this way, reaches us first, sometimes hours earlier. This is enough time to alert astronomers working with optical, radio, and X-ray telescopes to direct their instruments to a particular part of the sky where something very interesting is about to be seen. Called messenger astronomy, combining observations via gravity and multiple parts of the electromagnetic spectrum will give scientists ways to observe and understand the universe in ways never before possible. For us, the coming years promise to be very exciting indeed. Have a great day, MacLaren.